All right, so we're going to look at some word problems that have equations that are similar to the ones that we were solving yesterday. All right, and they kind of fit into a few different types of categories. And if you're doing physics, some of this will seem familiar. If you're not, hopefully it will help you feel more comfortable with physics when you get there. The first group especially, because we're going to look at speed, time, and distance. So here's an example. The average speed of a car is 3 times the average speed of a cyclist. It would take the cyclist 20 hours more to travel 900 kilometers than the car. Find the average speed of both. Now, we're really talking average speed because it's difficult for a vehicle to go a constant speed the whole entire time, right? You slow down for corners, you slow down for traffic, pedestrians, hopefully, etc. So whenever we're talking about speed, we're talking about average speed over time. So we're looking for basically the speed of the car and the speed of the cyclist. What is the relationship between speed and time and distance? We actually know this, we just don't always know that we know this. So if I was driving 100 kilometers an hour and I drove for 3 hours, could you tell me how far I drove? So what's the relationship? If I drove 100 kilometers for 3 hours, how far did I go? Wake up, folks. Yes?
Speed is the definition of the distance you get within a lifetime.
Okay, so write that as an equation. How would we write it?
Speed is equal to distance divided by time.
True, but let's do it as a product. So distance equals speed times time. So D equals ST, or if you prefer, VT, velocity, right? Now, Reese, what you were saying was that time is distance divided by speed, and speed is distance divided by time. Those are all the variations of that same formula. But the base or root formula, if you will, is this one here. That if you take your speed and you multiply by how long you're going, you'll figure out how far you went. And we know that intuitively when we're awake. All right, so I always attack these problems by setting it up in a little bit of a table or a chart, because I just find it helps to organize your thinking. So I'm going to put my cyclist and my car, and my chart's going to have 3 pieces. It's going to have speed, time, and distance. All right, so what am I looking for in this question? What am I being asked to find? Bo, are you paying attention? Bo, are you watching? Good. Can you put the phone away, please? Phone, away. Your phone? Yes, off. Thank you. Okay. So what am I looking for? speed. I'm looking for the speed of the car and the speed of the cyclist. So that's where my variable is going to go. What you're looking for, that's what you make your variable. All right? So I need to come up with, I don't want to have two different variables. We're not doing systems. You want to relate everything to one variable. So how can I relate the car's speed and the cyclist's speed using one variable? Which one would you make x? Emily?
The cyclist speed.
Okay. And then how could I relate the car back to that?
The car is 3 times faster.
So
3x.
3x. Beautiful. Because the car has a speed 3 times greater than the cyclist, then I write that as 3x. All right. Now, let's leave time for a moment. Do I know distance? 900 kilometers. It is the same for both in this example. It won't always be the same, but in this example it is. All right. Now, I don't want to introduce another variable, and I don't know anything about time. But I can write time in terms of distance and speed. So if we look at the second variation of this formula that we wrote down, I'm going to write time using the distance and speed that I already have written down. So my time is my distance divided by my speed. So now I have an expression for time using the information that I already had in my chart. I don't want to introduce a second variable. So I can do everything in terms of x. All right, now I have all of my variables and all my expressions for all my unknowns. I need to write a formula, or sorry, an equation. So there's one piece of information that I haven't used yet in the question, which is what? Yeah, I haven't used this statement that says it would take the cyclist 20 hours more to travel 900 kilometers. Okay, so that means that the cyclist's speed is what in comparison to the car's speed? No, sorry, not speed. The cyclist's time is what compared to the car's time of travel? It's 20 more, right? So the time of the cyclist is 20 more than the time of the car. But I want to write an equation. I want to make them equal. So where does that 20 go? And what do I do with it to make these two sides equal? Yep?
You add it on the left side, and the equals 900.
Do you want me to add it here? Does everybody agree with that? Remember, this is the cyclist time. And this is the car's time. And we said that the cyclist time was 20 more than the car. Okay? So you've now made it 40 more than the other side. Haven't you? Right? Because this was already 20 more. And we try to make them equal. So you've added 20 to the thing that's already bigger. Right? I want to make this side equal to this side. If this is 20 more than this, I don't want to add 20 here. I want to add 20 here. Or, since we already have it written on this side, subtract 20 hours to make them equal. I need to make them equal because they aren't equal to start with. Does that make sense? And that's the common mistake. I'm really glad you did that because we all do that the first time. So you really have to think, because this is 20 more, I need to reduce it by 20 to make it equal to the car's time because the car's time is less. Okay? All right, now we have an equation. And in terms of the equations we were solving yesterday, this one's pretty straightforward. So finish the question, solve that equation, and then answer the sentence or the question in a sentence because that's what you do with word problems. So everybody get 30 for x. All right. So the cyclist time is 30 hours. Or sorry, not time. I gotta wake up. The cyclist speed is 30 hours. I think I'm ready for a holiday. Let's try again. The cyclist speed is 30 kilometers an hour. Here we go. And the car's speed is 90 kilometers per hour. Okay? Yes, Joy. I solved the equation. Did you look at the notes from yesterday?
Yeah.
Okay, so what we're doing is we're multiplying by the lowest common denominator, which was 3x,
Yeah.
so that we could divide all the denominators out. And when I did that, I got to that line. Okay? I can come and help you in a bit, because I know you missed yesterday, so. All right. Let's try another one. Don't think we're quite ready to do it on our own yet, are we? Okay. A boat travels (70 kilometers) up a river with a current of 2 kilometers per hour. Then 70 kilometers back to its starting point. If the whole trip took 12 hours, what is the speed of the boat in still water? All right, so let's just make sure we understand what this means. So if it was completely and totally calm, that's what we mean by still water, a boat would have a particular speed, okay? When you're going against a current, what's that going to do to your speed? It's going to slow you down, and it's going to slow you down whatever the speed of the current is. So let's say you were going 20 kilometers an hour. If you're going into a 2 kilometer an hour current, it's going to slow your speed down to 18 kilometers an hour, your overall speed, relative to the distance that you're traveling. If that current is behind you, what's it going to do to your speed? It's going to speed you up by 2 kilometers an hour. Okay? Similar situation occurs in the air when you're going with the wind and against the wind. Okay? Talk about a tailwind and a headwind. The tailwind is at your tail of the plane. It's pushing you, speeding you up. A headwind is in your face. You're going against it, it slows you down. So there's lots of questions that you'll get that will talk about currents or headwinds, tailwinds. They all work the same way. So we're going to set this up the same way we did the last question in a chart. And we're going to talk about going upstream and going downstream. And again, we have our speed, our time, and our distance. Now, before we fill out the chart, what is it that we're looking for? What's the question asking us to find? Okay, so I'm going to let x equal the speed of boat in still water. Okay, so what is my speed when I'm going upstream? I need to come up with an expression for my speed in going against the current. Upstream is against the current. Andrew?
X minus 2.
X minus 2. And downstream? X plus 2. Okay, skip time for a minute. Let's go over to distance. What's my distance that I travel upstream? 70 kilometers. And downstream? 70 kilometers. All right. Now, just like I did before, I'm going to take time and I'm going to write it as an expression using distance and speed. So how can I represent my time going upstream? Correct. 70 over x minus 2. And my time going downstream? 70 over x plus 2. All right. Now I have an expression for time. Now the second part of my question tells me something about the time. Okay? If the whole trip took 12 hours, so that means all my time going upstream and my time going downstream has a total of 12. So how do I write that as an equation? Write it down. Take your expressions for time and write an equation that indicates or shows or demonstrates, models the fact that your trip took 12 hours. Question?
Yeah. Don't you have to make that complicated? Because it's actually upstream and downstream is an average case in the end, and you can just do that by 2.
Well, let's see if our answer works out to what you think.
Doesn't it?
I don't know. Let's see. I know intuitively I know what you're saying. It works a little different though, because your times won't be equal. You're assuming times are equal, but they're not.
Yeah, but we're just looking for speed.
Mhm.
We're not looking for the time.
Okay?
Speed.
Let's see.
Looking for the time, I would say, yes, we have to look at that. For the speed,
But speed is connected to time.
but it's the water, what reads the
Mhm.
average case. Up and downstream.
Okay, let's see. Hang on to that thought. So, somebody have an equation for me? Yes?
Upstream time plus downstream time equals 12.
Okay, so we need to write that as an equation. So 70 over x minus 2 plus 70 over x plus 2 equals 12. All right, solve that. Find for me the speed. All right, so we have to multiply everything through by the common denominator, which is x plus 2, x minus 2. How can you forget, guys? We just did this yesterday. That's true, you were not. All right, so my x minus 2's divide out, and I'm left with 70 times x plus 2. Here my x plus 2's divide out, and I'm left with 70 times x minus 2. And on this side, 12 and nothing divides out. And x plus 2, x minus 2, of course, is x squared minus 4. So I'm just going to write that just to save myself a step. Now I need to get rid of brackets. So 70x plus 140 plus 70x minus 140 equals 12x squared minus 48. These, of course, add to 0. And I'm going to bring the 140x over to the other side. This becomes negative 140x. And I can factor out a 4, at the very least. I can take 6 out? No? Okay. What's 140 divided by 4? 35. Yes. And now I need to factor that. So multiplies to negative 36 adds to negative 35. So I need to make negative 36 and positive 1. So x equals negative 1/3 and 12. So now I have two answers. So what? Is there two possible answers here? Correct. So I have one answer that's negative, and since x represents speed, and when you can't have negative speed, we discard the negative value, and so 12 would be our answer. All right? So the boat's speed in Stillwater is 12 kilometers per hour. All right. Okay, I'm going to go on to a different type of problem only because I'm looking at time and I'm worried that I won't get to the second type, which is, so you've got two examples now to look at and follow when you get to try and use in your homework. And if we have time, I'll give you one to try at the end. But I want to go on to a different kind of problem. So those are speed, time, and distance ones, and there's lots of variations. But if you set them up in that chart every time, I think you'll find that that really helps to organize your thinking. The second type of problem we're going to look at are called work problems. So here's an example. It takes Jerry 9 hours longer than George to paint a house. Together, they can do the job in 20 hours. How long would it take each of them to paint the house alone? All right. So whenever we're doing word problems, first thing we do is identify variables. So what is it we're looking to find? So we got Jerry's time alone and George's time alone. So which one do we want to make X? Okay, so we met George's time alone be X, then what would Jerry's time alone be? Yep. X plus 9. Beautiful. All right. So that part's not too bad. So let's focus on George for a moment. If George takes X hours to do the job, how much of the job does he do in 1 hour? Let's say it took George 40 hours to do the job by himself. How much of the job would he do, how much of the total job would he do in 1 hour? Yep? 1/40th. So since it takes him X hours, be 1 over X. So George can do 1 over X of the job per hour. And Jerry can do 1 over X plus 9 of job per hour. Okay? So let's stick with 40 for a minute. If George can do the total job in 40 hours, that means he's doing 1/40th of the job per hour. how much of the job does he do in the 20 hours that they work together? He'd do 1/40th of the job per hour. How many hours does he work? 20. So if I do 1/40th of the job per hour and I work 20 hours, or George does, yep. Yeah, he's done 20/40ths of the job, which of course is 1/2. Okay? So that doesn't change given that he's doing 1x of the job per hour. So he can do 1x times 20. He does 20x of the job in total. And Jerry does 20 over x plus 9 of the job. Okay? Together, how much of the job do they do? The whole thing. They do one entire job. They get the job done. So we take the amount that George does, plus the amount that Jerry does, we add it together and we have one complete job done. Okay? Takes a little thinking to get your head around this the first time. Any questions about that? So if you look at, basically what you're doing is total time, or time together, over time alone. And that's the portion of job each person does. All right, so let's solve this. Common denominator is x times x plus 9. So here my x's divide out, and I get 20 times x plus 9. Here my x plus 9's divide out, and I get 20x. And over here I get x times x plus 9. So I get 20x plus 180 plus 20x equals x squared plus 9x. So this is quadratic, so I'm going to set it equal to 0. So I'm going to bring that 40x over. So this is going to be minus 31x minus 180. So I got to factor that. Minus 36 plus 5. So x equals 36 and negative 5. Now, what does x represent again? Let's go back up to the beginning here. Yep. Time George takes a loan. So does negative 5 make sense? No. Again, we can't have a negative value for time. So we discard the negative 5. So George takes 36 hours alone. And Jerry, how long would he take? 45 hours alone. Now, if we wanted to check, we can see if this makes sense. 20 over 36 plus 20 over 45. And see if that equals 1. We need a common denominator to do that. Or we can use calculators and just plug it in. I would reduce first. Yeah, look at that. Reduce. It works. So we got one job done. All right. When are we done? 54, 56, 54? Okay. Let's try another one of these. See if you can set this one up yourself. So Jane works twice as fast as her daughter Anna if it takes them 15 minutes clean the kitchen together. How long would it take each of them to do it alone? All right, so try and set that one up. See if you can solve it. All right, so we let Jane's time be x, Anna's time be 2x. So Jane's gonna do 1x of the job per hour. Anna's gonna do 1 over 2x per hour. So if they're doing it for 15 minutes, then 15 over x plus 15 over 2x equals what? 1 whole job completed. So multiply through by 2x, that's my common denominator. Here my x's divide out, I get 30. Here my 2x's divide out, I get 15 equals 2x. Easy equation to solve. So Jane would take 22.5 minutes alone, and Anna would take 45 minutes alone. Okay? So that's all the time we got. I'm going to give you the assignment, let you get started on the first one. So tomorrow, let me just write this down first. Page 597, 602. So 10 problems. Try those.